Another application relates to elasticities, and if you can recall, we did this in chapter 5, and we saw that if we have this function, which is the demand function, d of p is equal to 8000 p raised to the power minus 1.5. And here, if you can recall, we showed that the elasticity of demand with respect to price is nothing but p upon d multiplied by d prime p, which can be written as this. And this was, in this case, if we calculate, it was minus 1.5. If I take up this expression and I take natural logarithms on both sides, so that is going to give me ln d of p is equal to ln 8000 minus 1.5 ln p. And this is nothing but a log linear relationship between ln d of p and ln p. And what we see here is that this minus 1.5 is nothing but the slope of the constant slope of this log linear relationship. And minus 1.5 I know is also the elasticity. That means I see here that the elasticity of demand with respect to price is in fact equal to the derivative. In fact, I can say it is equal to the logarithmic derivative. It is actually equal to, so I can write d ln dp divided by d ln p. So this is in fact equal to minus 1.5. What we see here is that, and I know that this is nothing but the elasticity of demand with respect to price. So what we see here is that the elasticity of demand with respect to price, I know it is p upon d multiplied by d prime p. But from this, we actually see that it is also equal to the logarithmic derivative d ln d divided by d ln d, not divided by, I'm so sorry for that. The elasticity of demand with respect to price is also equal to the logarithmic derivative, which is d ln d over d ln p. And this we see is nothing but the slope of this log linear relationship, the constant slope of this log linear relationship. In other words, when we differentiate ln d with respect to ln p, what we get is the elasticity of demand with respect to price. And when I talk about d ln d divided by, not again divided by, d ln d by d ln p, this is the logarithmic derivative. It's also called the double logarithmic derivative precisely because we are differentiating ln d with respect to ln p. So this is called logarithmic derivative. And just to emphasize upon the fact that we are differentiating ln d with respect to ln p, we say that it is the double logarithmic derivative. And this is nothing but the elasticity of demand with respect to price. And in fact, there is a very important rule that when we talk about elasticities are nothing but logarithmic derivatives. So there is in fact a general rule that elasticities are logarithmic derivatives. I can also just put that brackets and write elasticities are double logarithmic derivatives. That is also correct. So these are logarithmic derivatives. And if I talk about, let's say two variables, x and y, and these are again positive variables, and the reason I talk about positive variables will become just clear. Here, let's say we have two variables, positive variables, x and y is a differentiable function of x. So let me write that. Y is a differentiable function of x. In this case, I know that if I want the elasticity of y with respect to x, I know that is x by y dy by dx. Now this is in fact equal to d ln y by d ln x, or in other words, I can think of d log y with respect to a and d log y with respect to a by d log x with respect to a. Here a is a positive base which we use for constructing logarithms. So what we are going to see here is that when we talk about the elasticity, as I said, elasticities are nothing but logarithmic derivatives. They are nothing but double logarithmic derivatives. And why we talked about x and y being two positive variables, because here we are thinking of this and this. We are thinking of ln y and ln x. So obviously y and x have to be positive. Keeping that in mind, so if you have x and y as two positive variables and y is a differentiable function of x, we know that if we want to calculate elasticity of y with respect to x, what would that be? That would be x by y multiplied by dy by dx, and this can then be written as d ln y by d ln x, which can also be written as d log y with respect to log y to the base a by d log x to the base a. Now a is a positive base that we use for constructing logarithms. Now I get to a very simple aside. Why am I saying that a has to be positive? Because let's just get back to what we studied in chapter 3, that if we have a quantity that is increasing by a fixed factor a per unit of time, that quantity is said to increase exponentially. Or if we have a quantity that decreases by a fixed factor a per unit of time, that quantity is said to decrease exponentially. That fixed factor a has to be positive. So that fixed factor is little a, and that is, let's say, this. That means I'm concerned about the exponential function f, which I define by this, capital A multiplied by little a raised to the power t. Both this and this, both capital A and little a, these are positive constants. And if this little a, if a is greater than 1, then f is increasing. But if a is between 0 and 1, then f is decreasing. The point to note here is that this little a, which we are concerned about, this is in fact what we are using as a base for constructing logarithms, and that's why we are actually concerned about a positive base, because we are anyway boiling everything down to an exponential function. And when we talk about an exponential function, we are concerned about a quantity that is increasing by a fixed factor per unit of time, or it is decreasing by a fixed factor per unit of time. And that fixed factor, which is little a, that has to be positive. If it is greater than 1, then the function is increasing. If it is less than 1 and greater than 0, the function is decreasing. So I hope now it's clear that this little a is a positive base for constructing logarithms. Why am I taking a as positive in this case? Now let's try to understand. So that completes the aside, and let's get back to the elasticity of y with respect to x. So the first This I know is x by y dy by dx. This is something I already know, but now let's think of dln y by dln x. And for that, just understand that if I'm concerned about dln y by dln x, this should actually turn out to be exactly equal to this. For that, we are actually going to apply the chain rule twice. Precisely because if I think of ln y, I know that ln y is a differentiable function of y. It is a differentiable function of y. That's one. And we know that y is surely assumed to be a differentiable function of x. That's what I have written here. Y is a differentiable function of x. Y is a differentiable function of x. Also, if you can see this, when I write x, I can write x as equal to e raised to the power ln x. Ln x is the power to which e has to be raised in order to get x. So x is equal to e raised to the power ln x, and in this way I can say that x is a differentiable function of ln x. So this is a differentiable function of ln x. And now I can apply the chain rule, and for that I can write dln y by dln x, which can be written as dln y by dy, because I know that ln y is a differentiable function of y. Then I can multiply it by dy by dx, because I know that y is a differentiable function of x, and then I know that x is a differentiable function of ln x. So I can then write dx by d ln x. Now I can calculate. D ln y by dy is equal to 1 by y. I just write dy by dx, and then I write and then I want to know dx by d ln x. For that I have to differentiate this expression with respect to ln x, and that gives me e raised to the power ln x. So this can then be written as 1 by y dy by dx x, which is equal to x by y dy by dx, and this is nothing but the elasticity of y with respect to x. So now it's clear to us that elasticity of y with respect to x is nothing but the double logarithmic derivative dln y by dln x. Now we have also written this, which is something different, but for that we have to just recall that. So now I would like to see that elasticity of y with respect to x, which is equal to x by y dy by dx, is equal to d ln y by d ln x, and this is equal to d log y with respect to a by d log x with respect to a. And now d log y to the base a by d log x to the base a. Now in this case I actually make use of this fact that log y to the base a is equal to 1 by ln a ln y. I make use of this, that log y to the base a is proportional to ln y, and the factor of proportionality is 1 by ln a. Now in this case what I now do is I also take into account the fact that if I want to write x, x can then be written as a raised to the power log x to the base a. So log x to the base a is nothing but the power to which a has to be raised in order to get x. And this again is a differentiable function of log x to the base a. So now we have the same story, in fact, that if I want to think of log y to the base a, this I know from here that this is a differentiable function of y it's exactly the same thing. Log y to the base a is a differentiable function of y. It's a differentiable function of y. Y is a differentiable function of x, and x I know is this. It is a differentiable function of log x to the base a. So now I can write d log y to the base a by d log x to the base a. This can then be written as d log y to the base a by dy. Then I can write dy by dx, and then I can write dx by d log x to the base a. For calculating this, let's get to this expression. I want to have d log y to the base a by dy. So this will be 1 by ln a multiplied by 1 by y. Because I know that log y to the base a is equal to 1 by ln a ln y. I want to differentiate this with respect to y. So I would have 1 by ln a 1 by y. Then it is dy by dx, and then it is dx by d log x to the base a. I know that this is the case. If I want to know dx by d log x to the base a, this is going to be equal to a raised to the power log x to the base a, and then it should be ln a. And in this case, if I want to see what this is, so if you can recall, what we are doing here is we are actually making use of the fact that if you have y is equal to a raised to the power x, dy by dx is equal to a raised to the power x, and it is this. And that's exactly what we are doing here. Y here, that x is log x to the base a. So if I want dx by d log x to the base a, it is a log x to the base a multiplied by ln a. And now I can write this. A log x to the base a ln a. Now these get cancelled. I know that a log x to the base a is nothing but x. So I get x by y dy by dx, which is nothing but the elasticity of y with respect to x. So now we have established that elasticity of, I can just write it this way, that now we have established elasticity of y with respect to x is equal to x by y dy by dx is equal to dln y by dln x is equal to d log y to the base a by d log x to the base a, wherein a is any positive base that we use for constructing logarithms.